actually in a somewhat bad shape. I mean, I flew through the night, and that was followed by 2 hours of Sao Paulo rush hour, so I'm in a somewhat delirious state now. The one thing I do understand is that I'm supposed to talk about SYK model, right? That's my job.
That's what you announced.
Yeah, so I will try to do that. So I will tell you a little bit more about what we will do, can do, but let me start by saying a few just philosophical words about SYK. So what is this SYK model? In case you haven't seen it, I mean, it's an amazing model. There's tons of different ways to think about it. What makes it so amazing is it's actually super simple. I mean, you can write it down in half a line. We will see it in a while. The way I personally think about the system is as a, if you will, a harmonic oscillator of many-body quantum chaos, in the sense that I argue there is no simpler model that displays the complexity or the richness of most phenomena that set many-body quantum chaos apart from single particle chaos. So the SYK model is really the minimum one, and at that I already mentioned it's ultra simple. You could, in a way, compare it to the Hubbard model. Yeah? Hubbard model is also a model of that size. You write it down, and there you have all the physics of many-body systems. But there is a crucial difference between the SYK and the Hubbard. The Hubbard is an unfriendly model. I mean, you can write it down. It's deceptively simple, but then you look at it and go to a computer. Or, I mean, we don't have very strong tools to get to terms with it. It's super complicated. The SYK model is a friendly model. It wants to help us. So it gives us a vast spectrum of I mean, massive tailwind, symmetries, and all kinds of tools, some of which we will discuss. And they go a long way in really analytically understanding structures of many-body chaos. So that's the pep talk in a way. I guess I will do this blackboard-wise. I mean, it's probably should work. I have some iPad notes. I'm happy to circulate them, but I mean, it's good to slow me down, so I write it nevertheless. So let me start. So there it is. I mean, so okay, SYK. The SYK model of what? Of many-body quantum. Can you read this? Yeah, it's okay. And again, I mean, same speech. If anything is unclear, immediately interrupt. Yeah, please. Of many-body chaos, body quantum chaos. Now, another disadvantage that I have, I mean, on top of my rush hour, is I just arrived. So I don't know yet the chemistry of this school. I don't know what you have learned. I talked a bit to Thomas Gur, but we have to synchronize, yeah, in some way. I just assume that at this day, every periodic orbit has been analyzed, and you have already quite some knowledge in quantum chaos. And if not, I'm happy to recapitulate anything I know. So what can we do with this model? I mean, I already mentioned it's a model with a very, very rich fundamental physics. Yeah, so we can study its fundamentals. Fundamental. And there is immediately a very important distinction to make, and it was mercifully made already in the previous talk. So I want to remind you of the following. This is a many-body model. We will see it in a while. But being a many-body model, there is particles around, and let's call them n. The number is n. Once we have that number, we can distinguish between two very different types of physics. And that's a super generic statement I make, which is by no means restricted to SYK, applies to any model. We can discuss what I would call short-time physics. Short time. And what I mean by short times are times of the order of n, or some power of n, or maybe even log n. Yeah? So n to the power alpha. What we have here is all the phenomena that were addressed in the previous talk, operator scrambling, chaotic instability, quantum butterfly, you name it, this type of physics. And the formulation becomes clearer when I distinguish it from the complementary regime, which we reach when we enter a time machine and go to timescales of the order of d. And I will, like in the previous talk, we didn't talk about it earlier, but my Hilbert space dimension is always d. And what we discuss here is physics of the timescales exponential in n, or maybe in a binary system, 2 to the n, but the 2 to the power n matters here. Yeah? And this is what I call long-time physics. Long times physics. What we look at here is timescales which are of the order of the Hilbert space dimensions, meaning energy scales which are super fine-grained and of the order of the many-body level spacing. So we can really look into structures of spectra or look at, fine structures of states, and all this takes place here. And from an applied perspective, from a fundamental perspective, and from a methodological perspective, these are totally different. Yeah? There's a gulf here in between, which we often don't know how to bridge. But what I want to mention is we should distinguish between these two. Now, that's the fundamental aspect. What I already announced, SYK is so nice and friendly that it allows us to address both of them to a very high degree analytically. And we can check against powerful numerics these days. So we are in a very strong position here. And people noticed, and then immediately it became clear that this must be useful also in a more applied context. Yeah? So what can we do with our SYK once we have understood its fundamental physics? And there are a bunch of application fields. They are overlapping, but I want to mention 3 of them, which are to some degree different scientifically, but also socially. Different communities. And they all love the SYK model. The one with which it arguably started, the SYK is now 8 years old, approximately, is gravity. Quantum gravity, it was Kitaev introduced this model having application in the physics of 2-dimensional holographic principles in mind. So there is this kind of gravity. Another one is you can think of the SYK, if you think about it, again, from a more like a quantum chaos perspective, the natural ends of the SYK aren't thermodynamically large. The ends which usually are interesting for applications are nuclear physics size large. The reason is, it will come, the SYK is an all-to-all interacting model, and in the universe, not everybody interacts with everybody, but in small-scale interacting compounds, you have this kind of mesoscopic nature. And this makes it a Lego block, or a little brick, for understanding the physics of strongly correlated matter, both in nuclear context, but importantly also in condensed matter. So what people love to do is to build granular models where the individual cells, are modeled by SYK models. And what's essential here is that the SYK model, if you think about it as a fermionic model, I'm announcing it's a fermionic model, it realizes actually a fermionic phase of matter which is strikingly different from the normal Fermi liquid, which we all know. It's a non-Fermi liquid. So it's the simplest model system for a non-Fermi liquid system, and as such can be used as a compound for modeling heavy fermion materials or other strongly interacting compounds. So there is this non-Fermi liquid physics, and this is quant matter. And then there is a third field, which again is overlapped to this one here, is also quant mat, but now with a shade, if you want, of info. And that's the physics of many-body localization, Fock space localization, and the corresponding entropy and information structures. So this, let me just write MBL, yeah, for many-body localization, and this is dominantly quant-mat, but with a little bit of info mixed in. And here we use the SYK as a, again, I mean, in the sense of a brickwork minimal model for understanding physics related to the spatial spreading of many-body wave functions in the presence of disorder. Good. So this is my little SYK universe. Yeah. Now, given the time frame, it's absolutely impossible to discuss all of this. It's just not possible. We have to make a choice. Yeah. And one choice I made for you, and another one I leave open. I took it, this is a school on quantum chaos and not on condensed matter, so I will put an emphasis on the upper half of the blackboard. And assuming, and I was right in that this will be already, this type of physics will be addressed in other seminars, I will put a focus to begin with here. So this will be, if you want, that's fine. That's part of my choice. Just a second. So this year is set. This we do. And the way I will go is actually, I mean, I won't introduce the SYK model for quite some while. What I want to do in the beginning, I want to stay today on a philosophical and somewhat vaguish level and discuss, or share with you, I should say, the ways, principal ways of understanding the long-time physics of many-body system in distinction to that of few-body quantum chaos systems. So this will be a half philosophical discussion, but it will we will arrive at some pretty strong conclusions from it, and without any kind of calculation, essentially. And then in a second part, I will introduce the SYK and see how this comes about in more concrete terms from this model. Yeah? And this will, I don't know how much time it will eat. I don't have a fixed program, so we can stop. We just see how it goes. But I will have time left once we are done through this. And then we can make a choice. One route I will offer is, this would be, I don't know, this would be one route to go, is use this here to discuss, if you are interested, holography and holographic quantum chaos. I mean, I think it's a super nice subject, and we have an expert in the room. So it's just a little bit off the beaten track, yeah. Particle physicists are very much in love now with quantum chaos, so we can discuss this, or I do this here in combination with that. So we discuss a little bit of OTOC physics in the SYK setting, how all this comes about. And then we discuss from there the emergence of a very nice non-Fermi liquid phase diagram in strongly correlated matter at minimal effort. I will not touch this stuff here today in these seminars. Yeah? So we can postpone the decision a little and see where it goes. I mean, for this I have a promised a very friendly talk, lots of pictures, and this year we can do on the blackboard this stuff. Yeah, this more or less the idea. Okay. So any more questions, comments? No, so far not. Now. Let me begin by, again, I mentioned it being a bit philosophical about general aspects of many-body quantum chaos. Aspects of many-body quantum chaos. And let me try to get away as much as possible without calculation. Let me already now make one statement, because there will come a point in the talk where you find all this quite unsatisfactory, and that's the following. In order to expose the full beauty of this here, I need an analytical tool, namely the nonlinear SYK model, in principle. And Thomas Guhr told me that he has introduced it, and it was on slide 257 I mean, so I checked this, 250. So this looked a bit heavy to me, and I can't go to this level of formality. So in principle, I need this model, but I don't need it in full formal detail. I need the mindset of this model. Yeah. So what I will do is I will try to sneak it in here, the idea of this nonlinear thinking, but not make it really formal. And it will be enough for me. You will find it a bit unsatisfactory because the discussion is somewhat vague. But the ideas you can all look up in Thomas. The hard stuff you can look up in Thomas' slides. So this is the part where I have to compromise. Otherwise, we will not get anywhere. Yeah. Okay, so let's do the following. Let's ask ourselves a question. Consider two things, namely two matrix Hamiltonians. Matrix Hamiltonians. And the only information I'm giving you is the following. The first is the matrix representation of a single or few body quantum chaos Hamiltonian. And I will always, in the following, when it comes to few body and single particle, I will use symbol S. Yeah. So we have a matrix HS, and that is the a one or few body matrix Hamiltonian. So you go to a computer and write down some matrix. Yeah? Number two is you take a many-body system, your choice. Think of a spin chain, randomness, something. And now, instead of doing second quantization, which most people in many-body physics do, you do first quantization. You write down the matrix. And in many-body quantum chaos, that's one lesson I learned over the last decade or so. It often pays to work in first quantized representations, to directly work with matrices instead of with C-dagger C and so on. So we write down a D-dimensional matrix, yeah, D is this, H, M. And this is a first quantized many-body Hamiltonian. Okay, and let me. I mean, just for hygienic reasons, let me just introduce this notation. Both HM and dimension D. Yeah. Yes, precisely. Exactly, just this. I mean, a big fat matrix. Yeah, I ask you a question now, and you already give. Let me, before we come to sparse, in this, this is about chaos, yeah? But in many cases, in many-body physics, and in particular in the SYK, the origin of chaos is disorder. So you assume that there is some randomness around, no matter where it comes from. And at some point, you may or may not average over realization. So for me, I don't distinguish here between deterministic chaos and randomness. So assume that in both there was some impurity or dirt around. You write down the matrix. Now, question to you. If I give you just this information, could you already tell me what are maybe differences between these guys? Is there some, so think there is some, think of a spin chain if you want. Yeah, you have a spin chain, lots of spins, a little bit of randomness sprinkled in. You go to write down the matrix. On a computer, you would do that. And compare that to the matrix of a billiard. What comes to mind? Is there anything we can say without any further information? Yes, very good. It's exactly. So we can actually, we can write down a picture that illustrates what you said. So if we make this a bit pictorial, that's the way how I interpret it. You suppose you have a billiard. I can discretize my space. So like such, I put it on a computer. And then I write down, and I call these sites I here maybe. And then I write down matrix elements Hij, which would be the overlap of some actual Hamiltonian J. And I think what you just said is that this is a short-range structure here, right? I mean, you have diagonal potential maybe plus a derivative operator. So it's okay. And we can also count the number of matrix elements we have. It's more or less of the order of D. I mean, it's a tri-diagonal matrix. Good. That's one thing. So, and let me also, maybe I can do this right now. I give you an example of the many-body system I have in mind. So spin chain, or whatever. I mean, some can be a free electron. Any model which is naturally quantized, again, in real space sites. But now we would write down a second quantized Hamiltonian, which has a generic structure, maybe some Ij, some, or maybe just I. But we could have some randomness. So here's some randomness. Ci dagger, Ci. And then there could be hopping term plus Ij, Vi, comma J, Ci dagger, J, and maybe interaction terms. So what we can do now, this was what you just said, we go to an occupation number basis. I mean, suppose these are fermions, each is occupied or not. Then we consider a basis of occupation number states, n, 0, 1, and write down H many-body. Now nm, this is not fortunate, but you know what I mean, yeah? I mean, or nn prime, let me write this. N, H, hat, n prime. And I think the way I interpret you here, it's not so easy to come up with a locality principle in general. There is some, and but there is no clear space-like metric here in this problem, at least none that is useful. That's one. But there is, on top of that, there is an order 1 effect, which is even more important, which I want to stress, which makes these two different. Any idea? Yeah, very good. I'm coming to that. It's a consequence of what I'm asking. So where does it come from, this Gaussianity? While here we are more used to, I don't know, not just big semicircle, but something with hard edges. It's a consequence of something. If I tell you, you will say it's all super simple, obvious. Okay, let's.
Yeah, first in the first case, even if you are like if you are on a localized basis and you make a change of basis, yes, you will get like a very random matrix.
Yes.
So
yes.
It's very like full, and you
yes.
get the typical
yes.
Wigner laws. Yes. But in the second case, even if you make a change of basis, you will get like a very sparse structure, and you cannot get rid of that.
Yeah, I kind of.
And that makes the like pretty much difference at the level of.
Yes, right. I was also thinking along these lines, and let me give you my view, but we can then compare. First of all, I wouldn't say that this matrix is more sparse than this. I mean, here we have one diagonal and next nearest neighbor, so it's also pretty sparse in the real space basis. Here, if you take one Fock space state, and you have d of them, there will be of order n nearest neighbors. Yep. So if you have local spin hopping, order n squared. So it's also we cannot meaningfully talk about diagonal, but there isn't a d squared matrix elements in this basis. Now the point I was wanting to get at is this Hamiltonian is much more entropic than this one. So here's much more randomness, and that we can figure out just by counting. So in a natural way model, you would have here at each side you have a random potential sitting. So you have of order d statistically independent matrix elements, statistically independent now, yeah, in your problem. Here, how many randomness we have here? Order n n squared. So we have a polynomially many, which is log d. So there is far lesser randomness and far lesser entropy here in this Hamiltonian. And this is, for me, at least, I mean, look, at least in my understanding, this is the order 1 difference, which makes, is responsible, and we will see how Gaussianity of density of states and different fluctuations and so on. Yeah? So what I would like to do in the following is essentially only allude to this principle, is more entropy here, lesser entropy here, in a hand-waving discussion, and from that we will then derive some conclusions on, say, how spectra look like in these different systems and how they are correlated. And then we can test all this against SYK. Yeah? And of course, I organize the discussion in such a way that the test works, yeah, later on. But first I want to discuss these things without model-specific assumptions. Good. So let me just fix this right here. I mean, the number of statistically independent random, how do you call it? I mean, elements or whatever. The number of statistically independent distributions entering the Hamiltonian is of order n to the alpha, which is logarithmic in D. And here, so if we copy and paste up here, it's generically order D. And and then there is another difference, and that connects to the previous talk. It was already mentioned here, we are sitting on some high-dimensional, relatively abstract lattice structure. We can define a lattice, I mean, some, say, hypercube like here. And in this space, there act these operators. And if you look at these operators, you will find that the majority of them actually commutes. Say if you take a typical Ci, Cj dagger, and then a typical Cl, Cm dagger, and it's large, yeah. So L and M are generically different from I and J. So most of them actually commute. And that is one of the strong, powerful principles that give you tailwind in the analysis of the SYK model. So you have a very low degree of correlations between these operators, as opposed to those here. When you write down, you can write down formal here, the generators which have zeros everywhere and 1 somewhere else. Most of them annihilate it actually, which is a very high level of correlations. That we will also understand I don't know of an elegant mathematical way of phrasing this. I just know from an applied point of view, this makes a major difference. And this is, I guess, maybe there's more, but this is what comes to mind on an order 1 level about differences. Now I want to come to, I want to mention 2 phenomenological consequences that follow immediately from this discussion without calculation. And then can you here? The first was already brought up. This high level of entropy, or better to say, the absence of strong entropy in the many-body case reflects in the nature of the many-body density of states. So these are generic phenomenological differences. The first is about the spectral density. Let me begin with S. Here, you all know, you must have heard it here, the spectral density of the simplest proxy of many-body quantum system. We have a Gaussian distributed random matrix, Gaussian matrix, is semicircular. This semicircle you've seen, right? And what I want to emphasize is that if you plot spectra as a function, average spectral density, as a function of energy, that you tend to find really super hard edges here, with maybe some tiny tails, and we will discuss them. But these tails are exponential in the Hilbert space dimension. So the spectrum is super rigid. In the many-body case, we observe much softer spectra. And in the center of the band, this is a zoom in yet, but in the center of the band, you actually have, it was already mentioned, you have typically a Gaussian density of states, not a semicircular one. And down here, if you zoom in, some edges, but they are generically much softer than here, and we will discuss this in some detail. And I personally interpret this as a consequence, again, of the relatively little randomness encoded here in this kind of operator structure. And a simple way to see this is as follows. I mean, to understand this. I mean, this smells like central limit, yeah? Central limit theorem in some way. So let's ask what are energy levels in the many-body case. And in the simplest case, where for a moment we switch off, we assume that we have here something and the rest we do later. You can focus on just this animal here to begin with. And then you would say that the density of states, I mean, is in a cartoon way, yeah, is say sum over VI NI in the occupation number representation, and this would be the typical energy of the level of Fock space number n. So what I want to emphasize is that generic energies tend to assume a form of large numbers of uncorrelated or not so strongly correlated numbers. And then you invoke central limit and you conclude, oh, must be Gaussian. If you find this too vague, I will derive this, or we will derive this, I'll give you an exercise for the SYK Hamiltonian a little later, how it comes about. But the essence of the argument is this. Well, that's one difference. Okay? Not so spectacular. Then I want to mention a methodological difference, which is also very important. How do we do, or how do we describe or make physical predictions concrete? One of our powerful methods is semi-classical analysis. I mean, periodic orbits, if you want. And there is a striking difference. This is concerns on the semi-classical treatment of Hamiltonians. Yeah. Yes. No, you're right. But nuclear physics size large ends give you already a very good. Yeah, it's an excellent point you're making. I mean, very good. For me, it's like in QCD3 is a large number, yeah. I mean, so if you, this argument is too stupid to dump. If n is 3, it will not work in this form. But if you take this Hamiltonian, have a few more matrix elements, you will see the absence of strong entropic correlations at work, and a central limit structure will emerge. Although I would find it more difficult to, so it's hand waving. Yes, it's yeah, but you don't sum over largely independent numbers in this case. In the V's are independent. Yeah. Yeah, but your energy is not a sum. You look here. What's in the background is that you have somehow n effective conservation laws around, and you will never have this in a single particle system because nothing commutes. So this argument is it's philosophical or not even that. Yeah, but. Yeah. But again, I mean, we will do a reasonably explicit and actually nice diagrammatic computation where this comes out. Right. Yeah, semi-classics. So semi-classics. Physical analysis. In principle, applicable. I mean, sometimes we don't have. You discuss it. Sometimes we have good classical limits. Like the Arno trajectories, but what I mean by that is we are concerned with actions which are much bigger than h bar, and then try to come up with some perturbative machinery that uses this largeness. And this is super highly developed in single particle physics, and we have the experts here, or some of them. And let me just remind you, let me just draw a cartoon and you will all know what I mean. So in single particle quantum chaos, we are interested in quantum interference phenomena to describe spectra or maybe transport observables, and we do that by drawing Feynman paths. We need typically a retarded and an advanced path to compute an observable, and then we see, oh, maybe it's this path, and it can to a very high degree interfere with this guy here. And Martin Sieber and Klaus Richter taught us how to count these, in at least for relevant model systems. Yeah, this I think you have seen in some semi-classical. Now, what about the M? And the way I think about it, and I don't know, Juan Diego, check me now on that, if this checks with you. Huh? You what? Yeah, no, never mind, bosonic fermi. The argument is general, I think, what I want to make. First point is, what we have here, say, in a two-dimensional billiard, what this here draws upon is that you have a sizable probability for a path going out, making a loop, say, in a diffusive medium and coming back. So there's a certain probability it will come back, and then it can self-interfere with another one which did something else. Here, we are living on a lattice whose lattice structure isn't even very clear, but one thing we can say, it's super high dimensional. Yeah? So if you think about any proxy of a super high dimensional system, the probability of starting here, then meandering around in the lattice, coming back after a long time is essentially 0. So there is no straightforward, for me at least, in single particle quantum chaos, we can actually sum over all these processes and make this a constructive tool. In many-body chaos, this is out of the question. So you might be tempted to say, all this semi-classics doesn't work, but this would be too naive. What I want to say is there are no long loops. It's this informal discussion. What I mean is these self-returning loops. However, there are many short loops, and exponentially more than in a single particle system, but lots of short loops. And we understand that we don't fully understand how this is crucial for the physics of many-body localization. Let me give you an example what I mean by a short loop. So suppose you have a spin chain, and you have this configuration here. Yeah? And now I want to go to a different configuration. And I think of this as one side on a hypercube. Everybody up, 1, 1, 1, 1, 1. Now I flip this guy. So I go to here. Here. And then I flip this one and end up here. And you probably can smell where it's going. No. This one. So this is not a loop, it's an amplitude, and I can compare that where I do this in opposite order. So this is a loop at Fock space. Yeah, right? If you send a magnetic field, you will have interference. And it's of these, if we anticipate, just as a way of thinking that loops are essential, interference loops are all what makes quantum mechanics different from classical mechanics. So the counting of loops is crucial. Then we realize here, oh gosh, there are lots and lots of loops and they can interfere, including destructively interfere. And we understand that much of the complexity, or in our absence of full understanding of many-body localization, the question of whether wave functions, many-body wave functions are extended or not in such systems, is related to an incomplete understanding of these semi-classical structures. Would you agree, Juan? Yeah. Okay. Yeah. I'm fermionic today. Okay. Good. Yeah. Come again? Yeah. Yeah, yeah, I was not very clear. By loop, I mean this whole thing. You can start here, go this way, this way, this way, and back. That would be a loop. And now suppose you want, this is an intermediate state of some more complicated analysis. Yeah? You start somewhere here, and you, oh, here, I'm here. Now, the guy can decide to make this loop, or make it in this order. It's a short loop, but it has a high phase volume. And that's why, and we don't know how to count them. Yeah. Right. And the reason is, of course, that this here, the analog cartoon would be, of course, here, that would be a crazy complicated lattice with a, I mean, this Fox-based lattice with a high coordination number. Good, so these are two main differences. Now we can ask, is there anything on the super universal level, without going model specific, which many-body and single particle quantum care systems have in common? And the answer is yes, a resounding yes. They have actually quite a lot in common. And the answer, or the keyword is long-time spectral statistics. So let me try to make this point. So what have H and what have M and S in common? And here comes an attempt of an answer. So let me look schematically at the many-body spectrum. I mean, I just make a dot for each level, and I assume that my spectrum ends somewhere. I just argued that the edge is soft, but I mean, let's suppose here we have a spectrum, and there is a minimal level sitting here. And if we do this on a computer, or when it all started in the 50s, I did this for nuclei, I mean, resonance scattering, you will find that there is a high tendency of these to be uniformly spaced. This is level rigidity, and this is something many-body systems and single particle systems have in common. And I want to find a language, I mean, a language which uses, or which makes this explicit. And I don't want to use the word random matrix theory, because we just argued for a many-body system, writing down a global random matrix is not a very good idea. So we need something else. And before motivating this concept, let me just introduce here some scales. So there is a many-body or single-body level spacing. And what I also would like to draw is, this is for one realization. And if we average over lots of these, you will find this here. Yeah, we find a uniformly a dense spectral set, which is non-vanishing down to some epsilon naught. This is a spectral boundary. Now, I just argued this guy fluctuates due to these Gaussian fluctuations, but what I want to argue is, somewhat confusingly perhaps, these fluctuations are not that of a global Gaussian, but they are generically, for many-body systems, in the M case, they vanish, these fluctuations are a polynomial in inverse ends. So n to the minus alpha, relatively large, but not super large. For a single particle system, they are of order d inverse, they are tiny. What they both have in common is that when I send n to infinity, they go away. So then I will have, in the n to infinity limit, for fixed macroscopic parameter, I will have a spectral edge. And I'm emphasizing this because this is the average spectrum. The way of thinking I want to sell you is I want to interpret this here as a quantum critical point of a symmetry breaking phase transition. This is this is Thomas Gur in light, yeah. So this I want to develop now, this qualitative picture, why this is a symmetry breaking phase transition. Once we have that picture, we can make many strong predictions on the spectrum. Yeah? So let me try to develop this. And I hope it's not too trivial for you, but first want to introduce some symbols, and then I want to remind you of symmetry breaking in magnets. And we write down a little dictionary, how symmetry breaking in magnets relates to this here, and what is actually broken, and what is the Goldstone mode, and all that, yeah? So how do we do that? So let's have in mind that ultimately we want to describe correlations in spectra. So we need to define a good observable to talk about. And what we describe our system through, in order to, yeah. Hmm? I make the point that I don't understand it.
Okay, but it's like in the case of many body systems, it will be lesser the contribution.
I actually don't know. I mean, if I'm inclined to say that in the physics, it depends on which physical questions we ask.
I was wondering if
Yeah.
I'm thinking now of the spectral form factor, right?
Yes.
You want to compute it either in the single particle case or in the many particle case.
Yes.
So if I want to have the ramp in the single particle
Yes.
case, I have to consider this.
For the ramp, you do Berry, you do this, yeah. And then you, yeah, yeah, this. Hmm?
But in this case, if
Oops. Yeah, yeah.
so in this case, I will have to, if like long priority are
Yes.
less important, these short terms will give me like initial decay. And so this like difference will be at the level of short time physics, right?
It's a super strong argument. And now, let me give you a hammer. I mean, look, if you ask me the following, you could press me and ask me the question, okay, yeah, you just made some philosophical remarks about semi-classics. In essence, this is this. I mean, compute the spectral form factor from your semi-classics, and if I say there is no long orbits, then the answer is there isn't any, which is clearly wrong, because we know that we have a ramp plateau structure. The thing is that included in this panopticon of scattering amplitudes in Fock space, there is one select subclass of amplitudes which, even the formulation sounds weird, commute with everything in ergodic mode. This is the Goldstone mode, which I'm now trying to construct. I do not have, and I wish I had, and I'm not even sure it's possible conceptually, I do not have a diagrammatic interpretation in this form of this mode, but what I do know how to do is to construct the theory of this mode and to gap it, I mean, against other contributions. And from that, I get the form factor in full glory. But I don't have a good, so since I do not understand this here constructively, I cannot go beyond that level. And I didn't promise everything's perfect, yeah, so this is the situation which we have. And in the SYK model, we can analytically construct this quantum critical theory, which I'm about, and it gives you non-perturbability with the form factor. But it's an excellent point. So how do we describe the system? We, in terms of green functions, of course, yeah? We are working in a first quantized representation. So we can write down resolvents and then compute their imaginary part trace. It gets density of states. So what we need is the following. Let's say we zoom here into some energy, not necessarily this one, somewhere into the spectrum. And then we write down this here. We can do that because we are working with a matrix, no problem. And I leave it open now, M or S, I mean Hamiltonian. But what's important is we need retarded and advanced green functions. And I write this in the following way, I delta, and now I consider a block of operator, that's why I put this hat here, tau 3. So +1, -1. So I have a two by two block operator which contains retarded and advanced green functions on its block. Yeah, is that clear? Okay. So let me write tau 3 equals 1 - 1. Okay, yeah. Somebody? Yes, most definitely. Thank you. Good. Now, what would you say happens if I average? I mean, what would be an approximate representation of this green function if I average over some randomness which is present here, such that instead I have maybe here some non-random part of the Hamiltonian left, but I did some averaging. What would be on order 1 level? I mean, what do you think is a good ansatz? What should I write here? No. Just the average green function on a computer, maybe. Actually, even a dumb question. What I want to argue is this here becomes a smearing, finite smearing. So your average, these are here sharply defined poles. And once I average, I get here some plus I gamma, and I don't care what this gamma is as long as it's finite. It's gamma, tau 3, but only if epsilon was inside the spectrum. For epsilon larger than epsilon naught. Otherwise, I retain here my I delta because there isn't anything to smear. Yeah? Is this acceptable? Now I want to phrase this in the language of a symmetry breaking phenomenon. This guy here has a symmetry under what? Under rotations in this 2x2 space. It's infinitesimally small. Unless I'm sitting right on a pole, there is no difference between retarded and advanced. Yeah? So this green function here, let me, G hat epsilon has a symmetry under T, G, T inverse, and T is element of U2. It has a continuous rotation symmetry. I didn't read all these Thomas Gur notes in detail, but he talked about supergroups, right? And he told you that supergroups have a compact part and a non-compact part. So this is the compact part of this supergroup. It's simply, and I will reduce the discussion to that. I mean, it's all we need to know is before averaging, we have a continuous symmetry around. Once we do our averaging, this symmetry is broken if and only if epsilon is larger than epsilon naught. So after averaging, we had of epsilon, let me say it goes to say T tilde. This is the maximal symmetry. And T tilde is in U2, if epsilon is smaller than epsilon naught, there's nothing happened. And it's in U1 cross U1, if epsilon is larger than epsilon naught. If we are larger than, if we are inside the spectrum here, you can still do a phase rotation in the retarded and advanced block independently. But instead of 4 complex degrees of freedom, you have only 2, so the symmetry is really down. And in this sense, I argue that this here is the quantum parameter, and it marks the quantum phase transition. And the quantum phase transition breaks the continuous symmetry, and the order parameter is this. And now you say, oh, this sounds formal. But there is a corollary to that. Every symmetry breaking quantum phase transition has Goldstone modes. And they are in your system, they are operational, they don't go away, especially at low energies in which we are interested. And it is these Goldstone modes which give us the spectral form factor and all that. Yeah. And not a what? No. Yeah, I'm saying there is a quantum phase transition here, and from here on until the end of the spectrum. Sure. Yeah, no. I mean, so suppose the spectrum is like this, when the symmetry is present here, absent here. No, not at all. No. I just want to tell the seemingly weird way of thinking about the situation, because for me, it's most powerful when it comes to actually understanding the fine structure of these many-body spectra. So what I would like to do is, I want to say the following. Yes, that's what they have what have M and S in common? Yeah, so look, I mean, let me tell you my own mantra. When you ask most people on the planet, ask what is the good signature of ergodic quantum chaos, they will say Boyer-Schmidt, or there is a random matrix paradigm. I mean, systems that behave as random matrices are chaotic. Fine. My own personal mantra is systems are ergodic, many-body quantum chaotic if they have this phase transition. And I don't know a single exception to that rule. So I think this is a very strong principle, in particular when it comes to systems that we don't understand very well. We should seek for this. If we go to the gravity route, I will discuss how you find this phase transition in a string theory. It's a very nice story. No. Oh, very good, very good. It's an excellent point. If it is metallic but integrable, then I can make this statement. But my Goldstone mode will not be gapped against. There is other hostile low energy fluctuating modes, which non-ergodic modes. No, sorry, I misinterpreted. Yeah. Yes, I mean, let me simplify the rules of the game. Let me compare two classes of systems. The first is a chaotic system, where I average over the randomness. The other one is an integrable system, which depends on a parameter. And I average over the parameter so that I again get a continuous spectrum. And now you could say in both cases there is a symmetry breaking, but here this will be it will be a stiff mode. I have just one. In the metallic system, there is lots of, different soft modes around, which fluctuate this stuff here away. Which, yeah, but it's a super important point actually. Yeah. Good. So here, we just pin down. Epsilon naught marks a symmetry breaking quantum phase transition. Quantum phase transition. The symmetry that is broken is U2. And if you remember magnetism, if not, I will recap it in a second. If you have an unbroken symmetry, and it gets broken down to U1 cross U1, then you have this coset here as a Goldstone mode manifold emerging. If you find this abstract, I make this more tangible in a second. Let me just say that this is a sphere. So you have a continuous mode, and in every theory of quantum chaos, at low energies, you have to integrate over it. In fact, you have to integrate over the corresponding supergroup. But once you do that, you get quantitatively the form factor and spectral correlation functions describing the microscale of the spectrum. Yeah? So this is our responsible mechanism behind it, are these fluctuations. And to make this more tangible, actually, for how long have I been talking? Yeah, that's fine, perfect, yeah. I can stop anytime. Yeah, but we can stop anytime. Yeah. By the way, this is the unsatisfactory part where I try to sell you this nonlinear SYK model stuff through the back door, but I need to go a little further along these lines for my purposes. So a small digression. How does the symmetry breaking work in a magnet? And then we write down a dictionary to quantum chaos, yeah? So suppose you have an SU2 magnet, means spin 1/2. Maybe a spin 1/2 quantum Heisenberg model on a lattice. So what we are talking about is essentially a lattice, and there's spins sitting here, like such. And that mimics the situation at high temperatures. So you're in a disordered phase of this magnet. And in this case, the system on average is fully rotationally symmetric in spin space, so you have SU2 invariance. This SU2 takes the role of this U2 over there. So invariance. Now you do two things. You lower temperature, and if we lower temperature, the spins will tend to order at a finite temperature this time, phase transition. But they don't know yet how to order, in which direction. So to tell them in which direction to order, you also want to apply an infinitesimal magnetic field to make them order in a specific direction. Yeah. So low temp. This is high T. Low T. And plus an infinitesimal magnetic field pointing in this direction, infinitesimal B. Then we have the following situation. We have a spontaneous symmetry breaking. So there is a magnetization setting in at a certain temperature M. Excuse me, there is a magnetization forming. And what we can write down is now the following. We can write down a few elements of a table, which I will then augment by the corresponding quantum chaos entries. So we have a magnet. There's a TC here, critical temperature. At TC, my spin expectation value orders. If you measure now spin operators, you will find an ordering. And if I choose my quantization axis such that B points in a Z direction, then this will be set by the direction of the magnetic field. There is a symmetry breaking taking place in spin space. So this is the space in which we consider our symmetry. And now comes the one non-trivial statement. There is a Goldstone mode. And the Goldstone mode, you know, is if I switch off B, it costs me no energy to rotate these guys. And the question is how to parameterize this in good ways. And the way to go is the following. If I organize my spin operator such that tau 3 corresponds here to this act, I mean, I choose this spin quantization axis as B, then a very good way to parameterize the spins is as follows. I take this tau 3 and I unitarily rotate it by T by an SU2 matrix. And if you do that, you obtain a unit vector establishing T. So these are now unitarily rotated transfigurations, and let me call this guy Q. I call this Q. So a statement here is these are our soft modes. Yeah? These are the rotation modes on the magnet at low temperature. And what is the space over which we are integrating here? It's U2 divided by everything that commutes with this guy, U2 over U1 times U1. So this is our Goldstone mode sector. And now I'm not knowing, am I boring you too fast, too slow, some combination? Because, I mean, it's not very exciting, but I would like to set up this kind of data to, any questions? but Goldstone mode you guys have heard about, right? In a magnet? Somewhere? No? I mean, okay, it's very simple. If you have a magnet at low temperatures, it looks like this. So you have a magnet on your desk or whatever. The spins point in one direction, but in which direction they point is totally arbitrary. So if you rotate them a little, all of them, you don't have to pay any potential energy. And these rotation degrees of freedom, they are called Goldstone modes. It's just their name. And they appear whenever you have a symmetry. Here the symmetry is confusing. Here it looks like less symmetric, but it's actually higher symmetric. Here this is on average uniform. Here you have broken the symmetry. Everybody points this way. But now you can rotate them. So all I'm saying is this is all you need to store away. There are some parameterization of these rotations. And this is just technical. I'm writing them down in this way. That's all that's happening here. Right. So we are almost done. There is one thing. If we turn on some finite magnetic field, the symmetry is, this is an explicit symmetry breaking. Yeah? If I make a strong magnetic field, so this is an explicit breaking of the symmetry. Finite B. It's an explicit symmetry breaking. And if this is so, and you write down the partition sum of the magnet, in the presence of a finite B, there must be some action, some thermodynamic action, which tells you what is this? I mean, how much do you have to pay? Yeah? And the action is a natural action is as follows: S is an action of Q. So Q doesn't like B. And the natural action you write down is, first of all, there should be an inverse temperature, because it's thermodynamics. Second, B should certainly enter linearly. So I write down here B. Then you have to pay the more, the stronger the system is magnetized. So B times M. And then comes something which tells you how strongly B is aligned with Q. And this guy wants to point in the direction of B. And if B is in 3 directions, you have this. And now you can write down a partition sum. If you write E to this guy, integrate over all Q's, you get a very good description of Curie-Weiss magnetism and all that. So this was the magnet. Yeah. And now we can ask ourselves, what are the corresponding phenomena in chaos? And once we have understood that, you know, apart from a few technical details, how to get the form factor for any chaotic system that is ergodic. So we can almost make this as a little quiz. What takes the role of TC? What takes, in this chaos context here, what takes the role of TC? What marks the phase transition? At phase, yeah, exactly. That's E naught. So at E naught, if you here you turn T and you get a phase symmetry breaking, here you play with E, and if your energy hits this point, you get a phase. Something happens, a phase transition. Now, what will take the role of average S? Once again? Yeah, I mean, right? So first of all, for S, for S, I give you immediately the answer. This is this green function matrix, this average guy, right? But it's almost identical question. What assumes the role of the magnetization, which I didn't write down here? Spin space. And we have here this magnetization. So this is the order parameter, actually. What is that? On the other side? Density of states. I mean, it's essentially, it's the average density of states. I mean, rho. So the onset of rho, let me write rho bar or whatever, is M. The role of spin space is now taken by a somewhat more abstract space, namely, it is this 2x2 space here. This is our rotation space, right? And we don't have a good name, we call it causal space, because it's about advanced retarded, so it's a causal space. This is retarded and advanced propagation. This is the Goldstone mode is written down in exactly the same way. I mean, we have this tau 3, and we can act on it with these T guys, and that's the symmetry out here, and it's broken here. So we again can write down the same thing. And what is now the explicit symmetry breaking? This I haven't told you yet. If we want to do spectral correlations, then we want to compare energies which are a little bit apart from each other. So what we need is actually a somewhat more general object. We need G plus of epsilon plus omega correlated, say, with G minus of epsilon minus omega over 2. So shifted green function, one retarded, one advanced, slightly different energies. And I can write this as epsilon minus h minus I delta plus omega over 2, tau 3. So I split here these energies a little bit up. So now we see that we have the symmetry breaking is not just this I delta, but also omega. Omega breaks this rotational symmetry, and hence it assumes the role of a magnetic field. So this is omega. And once we know this, we can write down immediately the action which we need. Namely, we write S of Q equals omega is certainly a player here. Then we get this trace Q tau 3. Fine. And now we need one scale that makes this guy dimensionless. What should we write here? Density of states. Right. And then we write an I. And that's the action of the nonlinear SYK model. So if you, yeah, it's causal symmetry that's broken. Yes, it's called, some people call it causal symmetry breaking. So this, what you can do is, you can open a textbook and where this is derived for all kinds of models. I mean, and then what I swept under the rug is that it's actually not just you, but the supergroup, but this is a technical detail. I mean, it's, for me, it has to do with the fact that we need to work with properly normalized correlation functions. So the actual guy here is a little bit more complicated, but for us, this is not so important. What is important is that this argumentation here is extremely general. In a metallic system, we would have here other fluctuation modes which fluctuate this way, but in a chaotic system, under a certain ergodic time, or Thouless time, or whatever, this is the dominant guy, and if you integrate over this in analogy to this partition sum, you get form factor, two-point correlation function, sigma 2 statistics. I mean, you get all these correlation functions. Yeah? And this was now a lot of talking. I just wanted to motivate that in our many-body systems, SYK model, this is a player. It is there, but it's not the only one. In a single particle quantum chaos system, you can often argue this is it in a kick top or a billiard. There is not much more than this. In the SYK model, there is a little more life here, in addition to this. And what I would like to do next, but maybe not now next, but chronologically next, or contents-wise next, is I want to store this away. This is what we always have. And now introduce, in addition to this, a second fluctuation channel, which exists only in many-body systems, and which has to do with this Gaussianity. And then we can marry these two, and we understand how many-body systems spectra fluctuate. And that will take another, I don't know, 15, 20 minutes, not now. And once we have that, we can then define the SYK model and test all this in the real system. So that's what the plan which I had in mind. Okay. Yeah. I think now would be a good time to actually stop. Maybe any questions? Yeah.
Thank you for the lecture. I just missed the last part. You said you were what you wanted to do next that adds to the many-body system.
Yeah. I give you a mental picture, yeah? So if you take an SYK spectrum, a single one, you look at this, the spectrum will look like this. And so there is a very strong degree of correlations. Once you have a level, the next one will be at delta, 2 delta, 3 delta. And this level, but not quite. I mean, they fluctuate a little. This information you get from this action. You integrate over this action, compute a spectral correlation function, and then you get something that oscillates here in this. I mean, the 2-point correlation function, which does this. This is all totally standard, but now comes the difference, which sets the many-body system apart from the... If you look at the next spectrum, it will again have this uniform structure, but the level spacing will be a little different. There will be, and this is like, there is like a breathing mode. These are these Gaussian fluctuations. There are these strong fluctuations sitting on top, and think of this like a like a masses coupled with strings, and you compress or expand the whole package. So there's a breathing and fluctuation mode, which is not captured by this action. So, yeah, good. This is this. I can only bullshit. I mean, this is this strong entropy. I mean, this the Hamiltonian is just too constrained. Too many different. But here, if you turn one knob in one of these V's, yeah, everybody starts to fluctuate, and they fluctuate in this kind of. Yeah, it's our collective mode. Yeah, Thomas Guhr actually loves them. I mean, in nuclei they exist. Also. In nuclei, they are really deformation modes, and so in all many-body systems we have them. And now we have to think of a good framework to describe this constructively. I mean, to describe the joint effect of them. And what I would like to do next is I would like to switch gears and focus on these collective fluctuation modes. Again, first in this more general framework, and then we make some predictions just based on this. How should spectral correlation functions look? Then we turn to the SYK model, and this we already have in the pocket, but I want to, for the SYK model, really derive these fluctuation modes. And we can then look at the combined effect of them quantitatively. I want to show you some numerical slides to see that it works. But this more or less the plan where this upper right-hand corner is concerned, right? Yeah.
Yeah. For example, if you want to deal with this kind of imagine a simple RMT ensemble of whatever kind of potential.
What is that?
An ensemble of Hamiltonians with an arbitrary potential,
yes.
Single particle.
Yes.
So if you want to, you have this kind of stuff called the loop equations for the resolvents.
Loop equations.
Yeah, that is like the.
You caught me. I don't know.
Are like the these ward identities for the resolvents.
What density?
The ward identities.
Oh, ward identities.
Yeah, ward
yes,
identity
yes,
for the
yes,
resolvent.
yes.
So this gives you like a big amount of huge correlation between the resolvents, and if you like manage to work through them, you can find some like specific behavior of the X of the. My question is, at the end you have here like an action principle,
yes.
right? So perhaps the ward identities of this like action principle can be like somehow related with this.
No, it's a brilliant question.
It's the same. Okay.
No, it's there. The ward identity is there, first of all.
Okay.
And it goes like this. If you take this action for omega equals 0, I mean, the ward identity, the ways I know, they zoom in at omega equals 0. So then you would tell, you can arbitrarily rotate here. Yeah? Okay. But you want to compute something from this action. So you need to introduce something like a source, I mean, to differentiate your partition sum, to get your actual Green functions. These sources generically break this rotational symmetry. So once you now ask, what is the effect of this rotation on these source terms, you find relations non-perturbative relations between, say, one-point function and two-point functions. So these are the Ward identities, and they have been, in fact, discussed under this name in this context. So this is a very good framework, Ward identity field theory, too. But they're there.
Thanks.
Mm.
Hey, Alex, thanks a lot for the nice lecture. Can it be that the terminology causal, the breaking of some causal symmetry, is more than terminology and actually eventually marks the emergence of kind of effective irreversible behavior?
No.
Okay.
Because, very good. I mean, the behavior is only fake irreversible because you don't average single green functions. If you average two of them, and that's in fact the physics of this symmetry restoration at small omega, the symmetry has to be there. So it's only broken at the mean field level. And at the mean field level, you see traces of irreversibility here. But when you actually compute a two-point function, you don't compute the product of these, as you know, but you also have correlations between them, which are described by these Qs, and then everything is reversible again. Yeah. Okay, thanks.
And a 2 for the colloquium here.